Okay, welcome everyone to our third meeting of the Evolved Stars and Systems. Today we have two seminars given by Jesús Toalá on carbon-rich dust in the evolved born-again planetary nebulae. And the second talk is given by Keaton Bell on the seismic technique of obtaining fundamental white dwarf parameters. And so Jesus can share the screen now. And I would like to remind everyone to mute themselves, if possible, except for the speaker.
Can you hear me?
Yes.
Okay. Thank you to the organizers for letting me speak to you about this very recent work that we just published early this year. It's about carbon-rich dust in born-again planetary nebulae, specifically in A30 and A78. So this is how A78 looks in a very recent APOD image. So what are born-again planetary nebulae, in case you missed it? So in some cases, very weird cases, apparently, when the central star of a planetary nebula is going descending the white dwarf cooling track, it might experience what is known as a very late thermal pulse. So basically what happens is that we still have the hydrogen burning shell, outer shell, which is producing more helium. So at some point, the helium shell may reach the conditions to ignite and to produce an explosion, a thermal runaway explosion of producing carbon and oxygen. So at this point, the helium may engulf the hydrogen burning shell, and then so the star increases its opacity in the surface, and then it takes back. So this is an HR diagram. So the star is taken back to the AGV, post-AGV region of the HR diagram. So at this point, so the subsequent evolution is fast, and then the star becomes an hydrogen deficient, Wolf-Rayet type carbon-rich star. And then this explosion, ejects hydrogen deficient carbon-rich material inside an old hydrogen-rich planetary nebula. So this is a very fast synthesis of this, what happens. It is a rare phenomenon in the sense that we do not see many objects that have experiences at this VLTP. Only a handful of objects have been characterized as part of this group of planetary nebulae. So here I'm showing you a few of them, 4 of them. So what we see is that the outer rich, more or less round planetary nebula, and then some hydrogen deficient clumps inside it, so expanded inside this planetary nebulae. So it is rare in the sense that it's also short. Star evolution models predict that it's a very short period of time in which the star is taken back to the post-AGV and it's reborn. It's something about 20 to 100 years, the whole evolution. But the thing is that as the star reduces its temperature below 10 to the 4 Kelvin, so these may produce very fast carbon-rich dust inside the planetary nebula. For example, I am showing you here the evolution of the Sakurai object, which is one of the most known and studied objects of this kind. It exploded like around 20 years ago, and the changes that has been experienced by this planetary nebula are dramatic. So we can actually see them year by year, the evolution. This is the spectra taken in the near infrared and then the medium infrared. Each line is a fit to the observed spectra. So you can see that the dust produced because of the formation of this carbon-rich material has been dramatically changes, and the dust has been increasing from 10 to the minus 10 up to 10 to the minus 5 solar masses. And the temperature has been evolving as well from something about 180 Kelvin to 1000 Kelvin. Other object, which is also interesting to mention, is Aval 58. This is a study presented by Clayton in 2013. And this is, you can see the observed photometry. And then different colored lines, which are, I think that these are black body models to try to fit the photometry. These authors suggest that the temperature of the dust is something between 75 to 800 Kelvin. And the total mass of dust is 2 times 10 to the minus 3 solar masses. I just want to mention that Aval 58 experienced a VLTP 100 years ago. So what do we know about Aval 30 and 78? So these were suggested to be uniquely infrared bright in this survey of more than 100 planetary nebulae by Cohen-Barlow in 1974. And subsequent studies tried to model or assess the dust in these objects. For example, this is a study presented by Cohen and collaborators in 1977. And so they predict that the dust has temperatures between 150 Kelvin and 160 for Aval 30. The observations did not have very good resolution, but they predicted that the dust might be present inside the old planetary nebula up to distances of 20 arc seconds. With time, so we started having higher resolution images, and in 84 and 1994, these people here presented the first images of the inner region of Aval 30. This is, you can see in the middle panel, this is the oxygen 3 image. This is the star is here. There's something like a disk, and apparently a bipolar ejection, one might call it. And the K band is only tracing this apparent disk. Looks like a disk, something like this. This was so far the image that was presented in the literature, the 1994 K-band image. But so we know also that these hydrogen pure nodes and filaments move at velocities between 40 and 200 kilometers per second, so really, really fast compared to the nebula expands, the outer nebula expands to something like 40. So this is the result of the very fast evolution of the central star. So the central star has now a stellar wind velocity of 3,000 kilometers per second. So it is pushing and disrupting this material ejected in the VLTP, creating these very nice patterns inside this old nebulae. So when measured or the abundances of the hydrogen pure in the outer nebula, these are very uniquely. We see, for example, here on the right panel, this is the spectrum of the outer envelope. You see the H-alpha line here, the oxygen lines here. And when trying to measure obtaining spectra from the inner clumps, this is the dense bright clumps here. This are the spectrum. So we do not see any hints of H-alpha, and whatever we see here, we can argue that it's because of the contribution of the outer shell, for example. So they're really depleted in hydrogen. Furthermore, a few years ago, we also studied these objects in X-ray with X-ray satellites. And again, because of the temperatures the velocities have 3,000 kilometers per second, it's very easy to produce adiabatically shocked regions. And what we saw in these X-ray observations is that the X-rays are also dominated by carbon-rich gas. So this is a spectrum, and we see clearly that this is dominated by the carbon-4 Lyman alpha line at 33.7 angstroms. So this is actually what we see in both of these planetary nebulae. So the problem is that relatively recently, some authors have suggested that these objects are not born-again objects, and it is more easily to explain their production of this hydrogen material by nova-like events. So here I show some of the prediction of the carbon to oxygen ratio. So some of the stellar evolution models studying this born-again event predict that this carbon to oxygen ratio should be larger than 1. So this is just a table I took from Marcelo's 2006 paper. And this is a couple of models they have, varying different physics in the modeling, and then comparing with other works. So in general, the carbon to oxygen is around 1.7 up to 3.5 times this value. But in 2011, Lau, DeMarco, and Liu, they started comparing the abundances obtained from optical studies from Aval 58 and Aval 30 with the predictions from NOVA and some observations of classical novae. So what they saw is that the carbon to oxygen ratio in born-again clumps, it's something about 0.06 to 0.3, and when studying the NOVA predictions, is something very similar, 0.05 up to 0.6. So this paper is a very nice paper, which they suggest that this is something to do with the binarity, because we more or less know that most of the central stars of planetary nebulae are harbor binary systems, or were formed because of binary systems. So this made more sense for them. But then again, if Aval 30 and Aval 78 are born-again objects, so where is this missing carbon? And the plot got even more interesting, because recently, or last year at JACB, they used Kepler observations and detected and suggest that the light curve variability they observed from the center star is because of the presence of a companion, a low mass companion, with a period of 1 day, 106 days. So it seems to suggest to support the NOVA-like scenario. But then the answer to this missing carbon question is of course the carbon-rich dust. So here so first what we did is to produce the high resolution images of the dust distribution of these two objects. On the top panels, I'm showing you Aval 30, and on the bottom panels, I'm showing you Aval 78. On the left, we have the oxygen-free line emission in optical. The middle panel is the mid-infrared color composite images. And then on the right, we compare the infrared in red and contours. In green, we have the optical, and in blue, we have the X-rays. So the first thing to notice is that the disk dust is coexisting with this very high temperature gas, which has a million degrees. I always imagine this as if we have a very hot soup and then we just drop cups of ice inside it. So this is what we are seeing here in these objects. And everything is, of course, carbon rich. So we took all of the available observations of photometry and spectra of Aval 30 and Aval 78, and this is how the spectral energy distribution looks like. In blue and black, we see Aval 30 and Aval 78. They're very similar. They have these bumps here, and then we, just for comparison, we also show the Aval 58 photometry here. So Aval 30 and 78 are almost like twins, as we've been saying for the past years. So we only produce a model for Aval 30, but of course, details of Aval 78 might vary a little bit, but I'm just going to show you Aval 30, the models for Aval 30 in this presentation. So what we did, we used Cloudy, which is the photoionization code developed by Fairlight and collaborators, and this is the 17 version, and which now includes the physics of the gas and the dust at the same time. And then we used PyCloudy to produce synthetic observations, simulating slits similarly as the optical observations and the photometry, infrared photometry. In our models, or in our test models, we use initially a dense inner structure, which has dust, and then this diffuse extended nebula, which will also have gas and dust. And then we didn't include the hydrogen-rich outer nebula because for us it's just contamination. And one thing to remark is that we are using the specific models of the stellar atmosphere of Aval 30. As I mentioned before, this is a Wolf-Rayet type central star, and these have very dense winds, and most of the photons are trapped in the wind. So we need to detailedly include this atmosphere. This was developed by the power people by Alcatel. So we need to test some models in order to assess which kinds of dusts should we include in our modeling. We know this is carbon rich, should be carbon rich, but which species we should use was the first question. So I show here various models. The yellow one is the amorphous carbon. The first thing to notice is that it makes good job fitting the photometry, but something between 10 and 30 microns is below the observed photometry. So the red line, which is graphite, makes a better job, but then at longer wavelengths, it goes below the observed photometry. Model C, which is the light blue, it includes fluffy amorphous carbon. This is because we know that interstellar dust is not solid spheres and it has structure. So, but the question is how empty we should start including these effects in the dust. So the answer is we don't know. So we started with a 50% emptiness, and this is the light blue here line. And then, of course, the best model is the combination of graphite and fluffy amorphous carbon here. Okay, so for A30, what we need is an inner dense disk, the extended nebula. No? And the abundances, we took the abundances reported by Guerrero in 1996 and Wesson collaborators in 2003. So this is our final model. This is a disk that includes graphite and fluffy amorphous carbon, and then the extended outer shell has fluffy amorphous carbon. It makes a good job in general, fitting the whole photometry. And here I just compared the different models, the test and our model, the final model. This is model E. This is the temperature of the dust versus the distance to the star. And we see that the temperatures are within the same range, but details vary depending on the species we use on the model. But model E, which is our disk model, is a little bit below what was estimated by previous studies. And of course, we see that the temperature drops with distance to the star. Different colors are different bin sizes in the dust. Okay, our model makes a good job fitting the photometry, the optical H-alpha flux of the lines, the electron temperature, and then we can estimate the total mass of the gas in this carbon-rich material. And we have something 4.4 10 to the minus 3 solar masses. And the total mass of dust, which is purely carbon, is almost 3.2 10 to the minus 3 solar masses. 33% of the total gas is in the outer shell, but 98% of the dust is in this outer shell. And our model requires the outer shell to reach up to 50 arc seconds, but almost entirely filling the whole hydrogen-rich planetary nebula. So we also test the emptiness of the amorphous carbon. How I just want to mention here that the more empty, the less mass of the dust we have, but the effective area of the dust is larger, so it can also fit the infrared photometry. So we estimated this as error bars, taking the 0 and 90% of the emptiness of the amorphous carbon dust. Okay, now we can compute the total mass ejected during the VLTP, which is adding just the total mass of gas and the total mass of dust. And this is something 7.7 10 to the minus 3 solar masses, with, again, 30% of these composed by purely carbon-rich dust. And now we can do our own estimations of the carbon to oxygen ratio using the optical abundances reported by Roger Wesson and collaborators in 2003. And this is the contribution from oxygen and carbon to the gas. But we need to take into account the dust, the carbon trapped in the dust. So this is purely carbon. So this is just adding the mass of carbon in the gas and the total mass of dust. And the ratio is something above 1.3 up to 5.6. This range depends on which is the mass we use for the amorphous carbon, depending on the emptiness we select. But this is larger than 1, and it could be up to 5 according to our models. So this is actually consistent with what the born-again scenario, which is very nice that we have been consistent all along. So as concluding remarks, I just want to mention that when trying to unveil the origins of these objects, we also need to take into account the carbon trapped into the dust, which has been proven because of the Sakurai's object that the carbon dust can be formed within a few years of the very late thermal pulse has been experienced by these objects. And now we can start questioning ourselves. So what was the role of a companion of Aval30 if it did not produce the born-again and the ejection of the hydrogen-poor material? Did it have a role producing this, I don't know, this explosion, or maybe it only helped like producing this bipolar shape we see in these hydrogen deficient material? So this is something that we still need to think about. And we are trying to do the same for other born-again planetary nebulae. So stay tuned. Thank you.
Thank you, Jesus. Are there any questions? Okay.
Oh.
Hi.
Yeah. First of all, thank you, Jesus. I mean, this is amazing. I mean, it was an amazing work. I mean, it's very interesting. The results are also very, very interesting. And not because they just fit the born-again models. No, that's also that's nice, but yeah, it's not. It's really a very interesting work. Mine is just a comment, I mean, because I already. I mean, I've read the work already, but you should. May I ask you like a question or a comment about one of the first slides that you showed?
Which one?
You know, when you show the work that you are doing with your student, I think the one with the future models.
Yes.
This is just, you know, I've been computing these models for that. That one. I've been computing these models for ages already now. So I have the feeling, I mean, maybe you would like to look at this, that there might be, I mean, this is just a hunch, so take it with a pinch of salt, but I have the impression that there might be something strange with the molecular opacities, let's say the low temperature opacities of the models, because the behavior of the models in the HR diagram, the way they go to the red, but not so much, and then they return like increasing the temperature, that looks as if something is happening with the opacities or something like that. So you might like to look at that in detail.
Okay, yes. Yeah, this is just a test. We've been using MESA in order to compute these models. So we are just running because MESA has a lot of parameters that you can twitch at the same time. Yeah. So this is just the first HI diagram that I took from the results.
Okay.
There's a lot of, yeah, I didn't notice specifically this. There's a lot of parameters you can play with in order to try to have different results.
Yeah, I know. Sorry,
yeah,
I know that because you told me that you were using the code, so that was why I wanted to point this out, because I know that you can, you know, select several choices for the, you know, opacity tables and these kind of things, and it's just that make sure that you're using later the right opacity tables for this composition.
Yeah, thanks. Yeah.
Yeah, that's it. It's just a comment. So, but the work was amazing.
Okay, there was a raised hand from Nicole, and then we have a question from David Jones, I think, and then Linda.
Yeah, for me also just a comment, namely that just because a star is variable, it doesn't mean that it's a binary. And from what I remember from the paper, it was not so easy to explain the variability because the amplitude is very small. With light curve models, I think you would need to have like a planet or something to explain it. And for now, we cannot really exclude that these hot white dwarfs have spots. And actually, we find that quite a significant number of white dwarfs shows photometric variability. So I would be careful with this interpretation.
Yeah, I just wanted to mention it.
Don't take it for granted that it's a binary just because it's variable.
Yeah, I wanted to mention it because it's the most recent paper on Aval30, but
So, sorry, Nicole, but the central star is a Wolf-Rayet type star. So it is not so easy to understand then what a spot means for it. Yeah? I mean, it has a strong wind.
But sorry, Helge, but wouldn't it be the same if you have like clamps of different temperatures in the, let's say, like fake photosphere of the star?
Yeah, I mean, there's the claim that something like spots also exist for massive Wolf-Rayet stars. Yeah, but it is so far not clear. I mean, you must imagine that there is not a hydrostatic atmosphere on top, but it is just an outflow of material. So how can there be something like a spot structure or so? Yeah. This is...
Okay, but I guess you don't need to be a spot like a proper spot. I mean, it's enough if you have like different temperatures, whatever is radiating, isn't it?
Yeah, okay. If you think about rotation and you have Van Zijpel theorem and something like this, yeah, maybe.
Okay. Thanks, Helge.
Okay, I think we are running short with time, so I'm sorry for the people that asked questions in the chat, and Linda, a list that raised a hand, but you can continue talking about this, discussing in the breakout sessions or write in the Slack channel. So I think the next one is now we're ready for Keaton, and thank you, Jesus, again.